Okay, so we are finally at the end of the course. We've covered all the material. We've covered a bit of extra material that I threw in because I couldn't face just going on with graph algorithms. I needed a bit of diversion. So we did pattern matching and group testing and fun stuff like that. So we're just going to quickly review the topics. I hope this is not going to take an hour and a half. Although we have covered quite a lot of stuff. Yeah, like 30-something hours of lecture videos. The goal is that after you watch this, the final exam should not be a surprise. Actually, the final exam should not be a surprise anyway, because based on the lecture topics, the emphasis I've given things, the questions I've asked in the assignments, you should have a pretty good idea. The midterm, the midterms from the fall semester, the practice midterms from two midterms from the fall semester, the two practice midterms from the fall semester, the practice final from the fall semester, the final from the fall semester, which was lethal, but the topics were right. It was just a bit hard. Sorry about that. To the fall class, two of whom are now your TAs. You can ask them if it were. I think everyone agreed it was hard. Even I agreed afterwards that it was hard. Didn't mean it to be that hard. So I'll try to make this one a bit easier. I will make this one a bit easier. I will ask people if it is easier. I asked people last time, and they said it seemed okay. Okay, let's go over what we've done. So, intro. That was just me saying what the shape of the course is, what I want you to know. There were certain things in there about, I want you to realize that we don't just study problems in isolation, that problems are related, that a breakthrough on one problem can have big effects on other problems. For example, if you speed up matrix multiplication, you speed up a whole load of other stuff. If you get a polynomial time algorithm for Hamiltonian path, then you get a polynomial time algorithm, worst case polytime algorithm for all kinds of other stuff. So we study the difficulty of problems, we study how to solve them, and by that I mean, yes, of course, when you actually get into it, you're really studying the nature of the problem, but there are general paradigms that you can use, such as divide and conquer, greedy algorithms, dynamic programming, and then stuff network flows, which we covered right at the end, but you don't probably have to know about, and except for assignment 6. And then you get into linear programming, and then you get into a lot of other stuff, quadratic programming, and stuff that you definitely do not need to know about, and we will not discuss so as not to distract you from the final. Right, okay. So that was the intro. Then we did Eulerian and Hamiltonian paths and cycles. So I wanted to hold up this example that said, look, okay, if you want to know if it's given a graph with vertices and edges, can you walk around the graph such that you cross every edge exactly once and get back to where you started? And the answer is, yes, we know how to do that. We know how to determine that. It's easy. And then you say, okay, well, can you do the sort of a very similar thing? Can you walk around the graph and visit each vertex once? And we're like, yeah, we have no idea how to do that quickly. And so the surprising thing is not that we can do the one or that we can't do the other, it's that we can do one and not the other, because they seem very similar. And one is easy and one is super difficult, and we can show that, if we could solve that, then we could solve a load of other stuff. So so that was an intro, and then we showed you, and I taught you Euler's algorithm for finding an Eulerian tour, and we discussed, okay, can you find an Eulerian path? Can you find stuff like that. And then we got into, so in lecture 2, we got into graph coloring and reductions. Remember, we showed that if you could solve 4 colorability, then you could solve 3 colorability because you just add this extra vertex and connect it to everything. That didn't work for planar graphs. And so we discussed, okay, so 3 colorability, I told you this is actually up to polynomial factors. This is exactly as hard as Hamiltonian cycle, Hamiltonian path or Hamiltonian cycle, because those are, and so, okay, so this doesn't look as much like Ham path as Eulerian cycles do, but it's equivalent up to polynomial factor. And I didn't show you why then, but it was because they're both NP complete. So, and then because divide and conquer, people think divide and conquer is just this introductory, beginning, easy stuff that you do. It's like, oh, it's just sorting. The only thing you can do with it is like sorting. That's the only stuff people use this for. No, it's actually, I made you do counting the 3 colorings of Nova Scotia, which is counting 3 colorings in planar, even just in planar graphs, is a sharp P problem. It's NP hard. Even if P is equal to NP, even if we know how to solve SAT, I don't think we know how to solve, how to count the colorings. We can approximate them. If we can solve SAT in polynomial time, then we can approximate the number of three colorings. But so this is quite a hard problem, but your programs should have solved it in a fraction of a second. Even just the program I gave you that did backtracking solved it in a fraction of a second. It's a pretty small graph. And I hope we all learned, I'm not sure I remember the counties of Nova Scotia, but I probably remember more of them than I did when I started this class. Okay, then we got right into sort of classic divide and conquer with Karatsuba's algorithm and Strassen's algorithm. So Karatsuba's was for multiplying numbers, n-digit numbers. Remember that we said, okay, addition is linear time in the number of digits if you're doing it as a human. But multiplication, then the naive method that we all learn in school is quadratic time. It's n squared, where n is the number of digits in each of the numbers. And can you do better than that? And I told you that Kolmogorov in 1960 or something conjectured no, and then Karatsuba came back and said, yeah, actually you can do it in sub-quadratic time. And Kolmogorov published it and stuff like that. Okay, and then Strassen's is sort of the same idea of cutting and doing these clever intermediate, remember with Karatsuba's you have x and y, and then you have these z1 and x0 and x1 and y0 and y1, and then you can compute z0 and z1 and z2, but z1 you do this clever way by multiplying and subtracting z1 and z2, and so you end up doing only 3 multiplications instead of 4. And with Strassen's, you end up doing 7 multiplications instead of 8, I think. I should check the scribe notes. We have scribe notes. Woo! Scribe notes for almost almost everything up to like here are posted. Almost everything. As of this morning. Not marked. I'm a bit behind on that. Sorry. But once I get this done, then I can disassemble my amateur recording studio and get my coffee table back, and then I can get on with other stuff, like marking scribe notes. And okay, so Strassen's algorithm is for an n by n matrix multiplication, and so you cut the matrices into each of the matrices into 4 pieces, and then you say, oh, okay, well this should take 1 by 1, should take 8, and then what you do this you use huge list of like these intermediate m sub something. submatrices, and then you end up doing 7 multiplications instead of 8, and you get an asymptotic speed. And of course, to get the speed up, you have to do this recursively. Then we talked about asymptotic notation, the master theorem, so remember asymptotic notation, big O, big omega, little omega. These are big theta, and we talked about these are sets of functions. So it's not best case, worst case. It's upper bound and lower bound. So you say, so you can use, it's math. It's something from math. It's not really just computer science. So it doesn't have to talk about an algorithm. We use it, for example, in approximations, where mathematicians say, oh, Stirling's formula approximates the factorial. I always use it for the log of the factorial. So yeah, it's the, is it the log? I think, is it the factorial or the log of the factorial? Anyway, I think it's the factorial. So they say yes. So Stirling's approximation is this. And so you say, okay, well, instead of working this thing out by doing all these multiplications, you get this, but then it's got this, like some lower order term, which is bounded to be at most constant times something. Okay, the master theorem was what you use generally where you do this, where you do what we usually do for divide and conquer, where you say, okay, well, we're cutting it into a certain number of pieces, and then you've got sort of the cost of the cutting step and how many pieces you cut it into. And so it was, remember, it was this, you cut it into A pieces of what size? So it's n over b plus some f of n. And you say, so f of n is sort of the cost of splitting and joining, a is the number of pieces, and b is the size. And so remember, we were saying, well, if you cut it into 2 pieces, why would it not always be so many pieces of this size? And remember, for Strasson's algorithm, you're saying, well, okay, you cut it, if you take a square matrix and you cut it, you get n over 2 by n over 2, but you get 4 of them. So that's why A and B aren't always the same. And so the master theorem, you plug it in, and there are these 3 cases, which depend on, which is the most expensive thing. Is it the splitting? Is it the joining? I mean, are you splitting into a lot of things, in which case the cost is dominated by the number of leaves? Or is the cost dominated by the joining? And so you have these cases, but it deals with most of the common stuff that we end up with. It is not, you cannot apply it always, but it will deal with a lot of the stuff we need. Okay, so moving right along, so then we did the analysis of merge sort and quicksort. So remember, merge sort was easy, quicksort is randomized, so we had to do this probabilistic argument, and that was on one of the assignments, so you should remember that. Also did quick select. Lower bounds for sorting. Remember, this was the argument about, okay, so this is where we saw Stirling's formula, so I should actually remember. But I spent the past half hour writing out these 2 boards, so I'm a bit, so remember we said, okay, so if you do, for example, a comparison-based sorting algorithm, each comparison you get sort of, if it's a binary comparison, you get a bit of information, so you can view it as a binary tree. So you think, okay, you do the comparisons. Well, when it has to have a leaf corresponding to each possible permutation that you started with, because you end up with an ordering. So it has to have as many leaves as there are orderings, so it has to have n factorial leaves. So how deep does it have to be? And log of n factorial, well, so you say a binary tree that has n factorial leaves has to have at least height log of n factorial. And so you say, okay, so that's going to be at least about n log n. So this is where we get this n log n worst case bound. And for comparison-based sorting. And we also talked about, like, okay, in special cases, for example, where you have a set of numbers, but they all come from a small range, then you can just sort them by direct addressing. So this doesn't always work. This lower bound holds for comparison-based sorting. And this is also where we use things like where I said, okay, you need at least about n log n, you need big omega n log n comparisons in the worst case. So see, that was on big omega, but it was in the worst case. So then we did, I did the sneaky thing where I said, oh, so we're talking about merging lists. So what about if we're merging lists, if like somebody hasn't understood the instructions, and we end up trying to merge a bunch of sorted lists, but they're not all the same size because our recursion broke down at some point. So we discussed this strategy. You know, how do you merge? If merging two lists takes time proportional to their total lengths, what is the optimal way to merge a bunch of lists of different sizes? And so we said, okay, so what would be what would seem to be the natural thing to do? Well, to do the cheapest thing first, which is merge the two smallest lists. And we argued that, yes, this is actually the case. And we used this optimal substructure thing where we said, okay, suppose that, remember we said, suppose there's, we can view the merging as a tree, and we argue that that it doesn't hurt you to if you view so each leaf is a list, and so if you have a big list that's lower than a small list, then you can move it up without increasing the total cost. And if you have two lists at the same level, then you can move them around in the same level without changing the cost. Two lists at the same level. You can move them around the same level without changing the cost. And so this said, okay, so if we say, okay, suppose there's an optimal tree, then we can move the two smallest things down to the bottom level, move them together, and therefore we do this argument and say, okay, if we do that, then we don't make this a mistake at this step. So what we're getting is this optimal substructure argument for greedy algorithms, which is suppose, so before we take any steps, our empty sub-solution can be extended to an optimal solution. Suppose that after I steps, our sub-solution can be extended to an optimal solution S. Show that after I plus 1 steps, using some kind of exchange argument usually, our optimal sub-solution can be extended to an optimal solution as our optimal sub-solution. Our sub-solution after I plus 1 steps can be extended to an optimal solution as prime. How do you do this? Well, if after I plus 1 you say, okay, well, I still agree with S, that's fine. Leave it alone. S is S prime. Otherwise, you say, okay, suppose that, so I could exchange these things. So I could extend my sub-solution after I steps to S. Suppose that I do this greedy thing and S does something else, then you do this exchange. Remember that gas station thing where you say, okay, you're trying to drive around, do a trip, and you're trying to stop the fewest number of times, and you have a map that shows where the gas stations are, and you think, okay, so the greedy strategy is obviously drive as far as you drive to the last gas station you can reach before you run out of gas and fill up there. To stop the minimum number of times. And you say, okay, well, what would happen if I drive as far as I can and somebody else stops earlier and fills up? And they say, well, okay, so I can do, after that, I can sort of steal their strategy. I can follow the same strategy, fill up at all the same places they do, because I filled up later. So I can do exactly what they do, and so I just exchange. They stopped earlier, so up to this point, up to this slightly earlier point, my solution could be extended to an optimal solution S, and then you say, okay, I drive I drive as far as I can, and they stop a bit earlier, and you say, okay, well, I do this exchange. And so you say, okay, whatever they would do from now on, I do that, but I just swap these two gas stations that where I stopped and where they stopped slightly earlier. We covered this a lot. I can't really go through it again in a review, but optimal substructure, good. Okay. So we did this for merging lists. Then we saw that actually this is Huffman's algorithm for building an optimal prefix-free code. Classic algorithm. I talked a little bit about Shannon and prefix-free codes and information theory and stuff like that. So this is a famous algorithm, but I think it's more natural to see it in terms of list first, because otherwise you have to understand what a prefix-free code is, and it's not that natural. It took Huffman a while to figure this out, whereas if you think of it in terms of lists, it's sort of easier, maybe. Okay, and then we talked about implementations of Huffman's algorithm, which usually people teach it in terms of priority queues, in which case it's n log n. However, if you have the weights sorted in advance, then you can do it with in linear time using two queues, using an algorithm by Van Leuven, which you had on the midterm, and maybe also on an assignment. I'm not sure. Okay, so that was the end of greedy. I mean, we saw some other greedy on the assignments, and we saw other greedy algorithms. So just remember, before we do any steps, our empty subsolution, blah, blah, blah. So then we got, oh no, this was still greedy. We saw that you can do fractional knapsack, which is where you can cut stuff to make it fit in your knapsack. The optimal strategy, the greedy strategy is optimal. When you take it by density, by profit, by value over weight, that ratio. And then we said, okay, so if the knapsack, if the items are uniform densities, so the value over weight ratios are all the same, then, and it's binary, so you can't cut the items, but then you take the biggest item first, then you get a two approximation algorithm, which means that you may not get an optimal solution, but you get something that's at least half the optimal solution. Remember? And this was because you say, okay, well, if I take the biggest thing, then if it's more than half of the more than half fills the backpack, then I have half the profit you can possibly get, because all the densities are uniform. And if I don't, then it was smaller than half. So that means that the next thing is also less than half. So I can keep taking stuff until at some point, when I stop, I must have more than half filled the backpack. And then we saw vertex cover, and we saw how to do vertex cover greedily in a tree. Remember, this was where you would pick a leaf and choose the other end of the edge, connecting that to the graph, to the tree, and you'd put the guard on, you'd choose the vertex at the other end. And that was optimal in a tree. And then we saw a two approximation algorithm for vertex cover in a general graph. Vertex cover in a general graph, so binary knapsack in general is NP complete. Vertex cover in a general graph is NP complete, but we saw a two approximation for that, where you would find a maximal matching, so you'd find a set of edges such that no vertex, a maximal set of edges such that no vertex was incident to two of those edges. So it's easy to find a maximal matching greedily, because as long as there is an edge such that its endpoints aren't touching any of the edges in your current matching, you just add it. And then eventually, when you can't add anything else, you're stuck. You stop. So it's maximal. So we said, okay, if you take a maximal matching, and then you take both ends of every edge in your maximal matching, so the vertex cover, so vertex cover is a subset of vertices such that every edge in the graph is incident to one of those vertices. If you say, okay, every edge in your matching must be covered, so one of its endpoints has to be in there, and none of the endpoints is covering 2 or more edges in the matching, so you have to have at least as many. The vertex cover, the optimal smallest vertex cover, has to have at least as many vertices as your matching has edges, and so you're going to take twice that many vertices. So you get a 2 approximation. You get a vertex cover that's at most twice the size of the minimum one. And you can do this with greedy. Isn't it? So it's like, we don't know how to do this optimally, but we can do it better than a 2 approx, I think, in polynomial time. But it's kind of cool that, it's pretty easy. So we see, like, there's a super hard problem, but we can get close. We don't know how to get in some cases, if it's a tree, we can do it optimally in polynomial time. And if it's a general graph, we don't know how to get it in polynomial time in the worst case, but we can guarantee that we can get close. So you can see that this is in algorithms 2 with Norbert. If you take it, then you'll find more ways to deal with NP-hard problems. Okay, so going right along, then we got into Kruskal's and Prim's algorithms. So this is greedy algorithms again, actually. So this is building minimum spanning trees. And we saw these 2. Remember, Kruskal's was you're allowed to, you build a forest, you have a forest. So you start with the vertices, and then you have the edges sorted, and you just have to sort them once. And then you always take, you consider the next edge in increasing order by cost. And if it creates a cycle, when you add it to your forest, then you throw it away. Otherwise, you add it. And then Prims, you have, so the Kruskal's maintains a sort of a spanning forest, and Prims is building a spanning tree. So you have a tree, and you always consider the edges that are currently incident to your tree, and you consider the smallest of these. And so for Prims, you do it with a priority queue. So for Kruskal's, it seems nicer, but then you think, oh, but we don't know. How do you detect if it creates a cycle? And so for this, we talked about the union find data structure. So this was sort of the first time that we saw it. Ooh, no, actually, okay, Van Leuven's priority queues. Okay, so priority queues, we had seen data structures speeding up algorithms with data structures. Van Leuven's, we're using 2 queues. But this time is the first time that I actually had to teach you a data structure that you hadn't seen before. Possibly the only time I had to teach you a data structure you hadn't seen before. So we did the union find data structure, which is super fast and super easy to implement, I hope, because I think I asked you to do it on the midterm. It's just really horrible to analyze. But I think the analysis in the book, but not the best analysis. The best analysis with this inverse Ackermann thing. I think the book just has the log star. And then we were done with greedy. We got into knapsack with dynamic programming. So remember, this was you consider, suppose that we have integer weights, and we have. So the easy one case was you say, okay, you have an infinite supply of each object, and now you ask, what do you do? How do you fill up the backpack? And you say, okay, well, you build the array. Excuse me. You build the array that's sort of from 0 to the capacity of the backpack, and then you say, okay, for each weight between 0 and the capacity of the backpack, is it possible to obtain that weight? And you compute this from 0 up to the capacity of the backpack. What is the optimal value that you can get with exactly that weight? And you compute this by looking at by considering all of the weights of the objects and looking and saying, okay, well, if I take this object, then the best weight I can get taking this object as the last is the best profit I can get for this weight minus the weight of the object plus the value of the object. So remember, this was when we were saying if your friendly professor will tell you the answer to everything except the actual, so it will tell you the answer to sub problems. He just won't tell you the answer to the full problem. So you say, okay, if I can solve this for smaller instances, so if the professor will tell me the answer for smaller instances, can I use that to work out the answer for the full instance? So knapsack with DP, but then I said, okay, so I just showed you something which it runs in time, like polynomial in the number of objects, and you have this array and its size of the capacity. So how is this? But I've told you that this algorithm, that this problem is hard. This binary knapsack is hard. We don't know how to do this. And I just showed you an algorithm that runs in time polynomial in the capacity, in the number of objects and the capacity of the backpack. And so remember, I said, okay, well, suppose, remember, you may have heard that that factoring, we don't know how to factor large numbers quickly, and we build crypto systems on the assumption that you can't. And then, but I made somebody give me a program for factoring a number n in time n. Right? It was just a for loop saying, like, for I from 1 to n, if I divides n, print I. And so this runs in time on a RAM. It'll run in time linear in n. And I said, okay, so this seems to be very fast. What is this problem? And the thing is that when we talk about polynomial algorithms, we're talking about, are they polynomial in the size of the representation of the problem? And when you give a number, you generally give it in binary. So you don't represent n with n copies of 1, which would be the unary representation. So when I give you the capacity of the knapsack, I'm going to give it written to you in binary, and so the array that actually goes from 0 to the capacity of the backpack, that's exponential in the size of the binary representation of the capacity of the backpack. So there are these two classes. NP hard in the strong sense are problems which remain hard even if you get the inputs and the numbers are written in unary. NP hard in the weak sense are problems that can be done generally by dynamic programming. You don't need to know this for third-year algorithms, but weak sense means that it's like knapsack. If you're given the numbers written in binary, then it's hard. We don't know how to do it in polynomial time, but if you're given the numbers written in unary, then yeah, you can do it in polynomial time in time polynomial in the actual numbers instead of their binary representations, which are logarithmic. Okay, so just good to know, but not really important for like right now. Then we did a linear time algorithm for max sum subarray. And we talked about, or I think there was an assignment question about, like, okay, what is the implication for max sum subarray in a circular array? And we said, oh, well, because we could reduce one to the other in linear time, then having a linear time dynamic program maximum subarray algorithm means that we can automatically do maximum subarray in a circular array also in linear time. So this was, and then actually, because you have to look at everything, you actually know that the question was actually asking, so what can we say about both of these? They're both theta n time. Okay, then we got into edit distance. Remember, this was, I did this graph, but like this sort of snakes and ladders-y thing. No, just ladders. Where you had these arrows and you're saying, okay, you could cross the arrows for free. So moving vertically and horizontally, and you say, okay, so how do you have this grid and you have these red arrows, how do you work out the cost of the minimum path of getting to here? And you say, okay, well, again, this idea of if you can ask your friendly professor, like, okay, can't use the board, from the top left to the bottom right, and you can say, okay, well, the friendly professor will tell me the cost of getting to all of the squares right above and above to the left and to the left. And from that, you do this minimum plus, well, to come from the one above, it costs you that cost plus 1. To come from the one to the left, it costs you that cost plus 1. And then to come from the one above to the left, it costs you that plus 1 if there isn't a red arrow, or that cost plus 0 if there is a red arrow. So this game, it was pretty easy, I hope. It wasn't too complicated. And then I said, okay, so actually, why was I teaching you this stupid problem? Because actually it's edit distance. If you just write the words, the two words along the top of the grid and the side of the grid, and the red arrows are where the characters match, then that dynamic program does edit distance. And then we got into optimal binary search trees. Remember, you're saying, okay, so if your friendly professor will tell you, you'd say, okay, you have 10 keys, and your friendly professor will tell you the cost of the optimal binary search tree for a consecutive subset of like 5 keys, but not all 10 keys. How do you find the cost of the optimal binary search tree for all 10 keys? And how you do this is you loop through for every possible way to choose the root, and then you say, okay, so if I choose the root to be the 6th, then what is the cost of the optimal binary search tree for the first 5, and what is the cost of the optimal binary search tree for the last 4? 7, 8, yeah, okay. And then so you loop through, and then we got into this Knuth speed up, where he said, okay, you actually only have to go from the adding things to the right, cannot make the optimal choice of the root go left. And so actually, naively, this takes cubic time, and with Knuth speed up, this takes quadratic time. And I put that on an assignment or on the midterm, I forget which. On the assignment, it was with probability for the misses, or the other way around, I forget. But yeah, everybody should remember optimal binary search trees. Probably not with a lot of love, but is cool. So then we did longest increasing subsequence, where you remember, if you do this without sneaky data structures, it takes quadratic time. And if you do it with this data structure, where you can say, oh, okay, of all the things I've seen before, what is the one that that is less than 7, that has the longest chain ending at it? So you can ask a range max query. And if you have a range max data structure, then you can do it in n log n time. So this is still dynamic programming. And then And then we did a midterm review, which actually I could have skipped this because I did the midterm review already. So I already said all this stuff. But look, so we're up to 40 minutes. So this is actually, so I should speed up because now we have to get through the rest of this and then I have to describe what's on the other board. So then the midterm, we were finished with divide and conquer, greedy, and dynamic programming. We got into NP completeness. So we did more reductions. Yay. So easy reductions. So start with clique and independent set reduced to each other. Independent set and vertex cover reduced to each other. Easy, easy. 3-sat obviously reduces to sat. And then we showed that Satan transforms. So sat reduces to 3-sat. And then we showed that clique reduces to sat because we didn't use Cook's theorem to do this because we hadn't seen Cook's theorem. Instead, we actually wrote formulas saying that a graph is has a clique of size k. Fun. And then so clique reduces to sat, sat reduces to 3-sat, and then we showed that 3-sat reduces to clique. So given an instance of 3-sat, you can build a graph such that the instance of 3-sat has a satisfying formula if and only if the graph, and you get a k, where k is the number of clauses in the 3-sat formula, such that the 3-sat formula is satisfiable if and only if the graph has a clique of size k. So these are all equivalent up to polynomial factors. If you can solve one, you can solve them all. And then we showed that ham path reduces to sat, again writing formulas for saying that a graph has a Hamiltonian path. And then we did the same thing for 3-colorability, writing a formula basically saying that that the graph has a 3-coloring. A formula that is satisfiable if and only if the graph has a 3-coloring. And then we showed that sat reduces to ham path, which I actually managed to mess up because I did the reduction to directed, and I forgot that it's pretty easy actually to do the reduction from directed to undirected. So I've left that out here. I messed it up, but it's online. It's on Wikipedia. It's just, I forgot I needed it, sorry. And we did the sat to 3-colorability. Remember, this is saying, okay, for each clause we have one of these gadgets, and which looks like a little circuit, which has these little triangles, and so this, we draw a graph that has a 3-coloring if and only if the formula is satisfiable. And then we did Cook's theorem. We did it with sort of, where I was saying, okay, so we did it with assembly, actually, first, because I was saying, okay, so to show that sat, you can give an assembly program that if you say, okay, does it accept in a certain number of steps, you can write a formula that sort of says this. So that's what we were doing here. We were practicing using propositional logic as sort of like a language to say something about other things like graphs and now programs. So like we were using it like a programming language. And so we showed that we could write a program. We could write a formula that said like that talked about this program and whether or not it would accept. And so we said, okay, so if you can write a C program that so it will accept in polynomial time, if it will check a solution to one of these problems, then you can say, okay, is there an input for this program that makes it say yes in polynomial time? Well, you could convert that into assembly, and you could say, okay, you can write a formula such that this formula is satisfiable if and only if this program has an input that makes it accept, which means, and the program is checking that the input is actually, for example, a 3-coloring of a certain graph. So you can say, okay, in that case, so if we can answer sat in polynomial time, determine if a formula has has a satisfying truth assignment, then we can tell whether this program has an input that makes it say yes in polynomial time. And that way we can answer any question such that we can write a program that checks an answer in polynomial time. So this is Cook's theorem, basically, except Cook was talking about Turing machines. So because you should know what a Turing machine is, at least a little bit. We talked about Turing machines, which are these things where you have this it can be deterministic or non-deterministic, and it has this finite state control. If it's non-deterministic finite state control, then it's a non-deterministic Turing machine. It has this infinite two-way tape, or one-way, doesn't really matter. And at each step it like reads a character and like writes something and moves left or right. Okay. I'm not going to put Turing machines on the final. Don't worry. And then just for fun, we did Cantor's diagonalization, the proof that the infinity of the reals is bigger than the infinity of the integers. So remember, the infinity of the even integers is the same infinity as the infinity of the integers. The infinity of the rationals is the same as the infinity of the integers, but the infinity of the reals is bigger. Okay, and we did that by arguing that the infinity of the reals cannot be put into one-to-one correspondence with the integers. So this is where this term diagonalization comes from, because the proof had, remember, we were taking one number from each of these. Supposing we had ordered the reals, we take one digit from each of them, and this is a diagonal. So that's what's diagonalization. So it's these self-referential mathy judo things where you suppose that somebody has an answer, and then you use that to break it. So the same thing with the halting problem. We say, okay, suppose that somebody had a program that could tell whether programs halted. Then you use that and you build a program that is a counterexample, where you say, okay, it halts if and only if it doesn't halt. So you use this program, and it's in the lecture. It's recorded, so you don't need to hear me saying it again. And then we did Kolmogorov complexity and showed that the size of given a string, computing this, basically all of these, it doesn't matter which programming language you're talking about, the size of the smallest program, it doesn't change except for an additive constant, which is the size of the compiler, the size of writing a compiler in this other programming language. But the size of the smallest, given us, it is incomputable. The problem. So the problem of computing the Kolmogorov complexity of a string is, given the string, say what the size of the smallest program is that outputs that string. So that's the Kolmogorov complexity of the string. It's incomputable, and we showed that it's incomputable by another diagonalization, by saying, okay, suppose that there were a program that does this, then we use it to find so we loop through the strings until it says, it has to say, for some string, it has to say it has a large Kolmogorov complexity, larger than the complexity of the program, plus a little bit of slack to do this little header thing. And so it loops through until it says that there is one of these strings has a large complexity, and then you say, well, actually, its complexity, this program, once it finds that string, it outputs it, and so that string actually has a complexity which is fairly small, which is the size of the program plus the overhead of doing this, looping through and finding this string. You also don't need to know this. You don't need to. You may want to, or you may not. But it's kind of cool to know that there are things, natural things you would want to compute that you can't. Okay. So then we got back into stuff you do need to know. Dijkstra's algorithm for single source shortest path, which doesn't deal with negative weight edges. Bellman-Ford, which deals with negative weight edges but not negative weight cycles. And then we did matrix multiplication. or something that looks a bit like matrix multiplication. So these are single source shortest path, and matrix multiplication. We were seeing that you can sort of count. Well, actually, in the next one we saw counting paths with matrix multiplication. I think I showed you. It wasn't exactly matrix multiplication. It was like instead of plus times, instead of the sum of the products, it was the min of the sums, I think. But okay, so you can use something like matrix multiplication for shortest paths. Then we did counting paths, and you had an assignment question on this, which may be due, which I won't talk about too much, because I think it's still, some people are still handing it in. Then we did Floyd-Warshall, and then as a bonus, because I was kind of sick of graph algorithms for a little bit, we did group testing, which is cool. And I stuck a question on just so that people would actually watch it, but is not usually in third-year algorithms classes. Then we went, and then we did topological sorting and strongly connected components. So this is depth first search, and those are in the lecture. Remember, so topological sorting, you're doing depth first searches, and you argue that okay, you look at the finish times and you sort by finish times, and you get the topological sort in a directed acyclic graph, a DAG. Strongly connected components, you have to do this depth first search. You do it once on the graph and then once on the transpose of the graph, but in this direction, breaking the order based on the finish times in the first DFS of the graph. And then we did network flows, which I recorded last night. So let's not go too much into that because it's still fresh and painful. What have we seen on the assignments? Assignment 1 was basically divide and conquer, which was lectures 1 and 2. Assignment 2 was an asymptotic analysis, master theorem, divide and conquer and greedy, which was lectures 3 to 8. Dynamic programming, A3 was basically dynamic programming, lectures 9 to 11. A4 was NP completeness, which was lectures 13 to 15. A5 was shortest paths, with one question on computability just because it's neat, which was lectures 16 to 18. A6 is topological sort, strongly connected components, and then because I just, we're getting to the end of the course and I was just getting distracted, I did, wait, did I say, oh yeah, pattern matching. I didn't talk about pattern matching here. So we saw super fast, what is pattern matching? We saw Knuth, Morris, Pratt. I skipped really, really quickly over Boyer-Moore. And then I talked a bit more about Karp-Raven because it's cool. And it sort of shows you things. So it gives me we haven't talked much about randomized stuff since we talked about quick sort and quick select. But Karp-Raven, you get into some neat number theory, and you see that, yeah, you can do these magic things where the chances, you do something and you can say, yeah, but the chances of this not working are billions to one, and so because people in algorithms, it's sometimes the case that it's much easier to get something randomized than it is to get something deterministic. And people think randomized is bad because it might break, but yeah, but the chances of it breaking are so small that, I mean, you could get hit by a bus. You're almost certainly going to get hit by a bus before Karp-Raven. If you use 128-bit hashes, you're almost certainly going to get hit by a bus before Karp-Raven lets you down. Well, you're working this out for either assignment 6, I think. Unless you're, okay. So worry more about being hit by a bus than Carp-Raven and the randomization. It's still, people still like, de-randomizing things because it's always nice to have a deterministic algorithm. But if the randomized algorithm is super simple and is almost certainly going to work, then, okay. So A6, we did topological sort and strongly connected components, and one question each on pattern matching, group testing, and network flows. Just because nobody's been asking me questions ever since I went offline, or at least nobody's been asking me questions. So even before, people weren't asking that many questions. Fewer than I got in the fall, so I've been speeding along and able to stick in a couple of fun things like pattern matching and group testing and network flows. Network flows you do get in third year in some places. In some places you get linear programming, I think, in third year. Pretty sure. Okay, I'm not sure which places. I'm not sure how many places, but some places. Some places actually network flows are part of the normal curriculum, and not just when the instructor is going too fast. So what was on the midterm? Divide and conquer. I was putting in an asymptotic analysis when I put this little insert. Divide and conquer, greedy, dynamic programming, and the counties of Nova Scotia as a bonus. So that was divide and conquer, asymptotic analysis. The master theorem was on there, divide and conquer, greedy, dynamic programming. So it was lectures 1 to 11. Okay. And 12 was the midterm review. So we now have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is pretty nicely split in terms of material. So the midterm divide and conquer, greedy, dynamic programming, counties of Nova Scotia. If you look, so it was the first half of the course. If you look at the fall final, which was too hard, it's on Brightspace. It's in the fall course folder. You can also find the practice final, 2 midterms, and 2 practice midterms. Okay? It was too hard, but it covered divide and conquer, asymptotic notation, master theorem, greedy, dynamic programming, NP completeness, graph algorithms. Surprise, surprise. Okay, so the assignments cover this, the midterm covers the first half of this, the fall final covered this. What is the final going to cover this time? Well, it's going to be 6 questions. The best 5 are going to count. There won't be coding. It'll be posted at 7 a.m. on July. Oh, by the way, in case this stuff is too small to read, I took photos of it and I'll post the photos separately. It'll be posted at 7 a.m. on the 31st. It will be due at midnight that night, Halifax time. Hard deadline. If something really bad, if you are hit by a bus or Carp-Raven fails you or something weird like that, then yes, of course, I'm going to be reasonable. But if you don't have a really good reason, then it's a hard deadline. So midnight, exactly midnight or after, once it is August, sorry. So I found out on the midterm, DAL does not want me to give you extensions on exams. So you're getting quite a long time. I didn't want to make it any later than this. I didn't want to make it from 7 a.m. to 7 a.m. because then people will stay up doing my exam and sleep through exams on August 1st. and this will make me unpopular with other instructors. So what's going to be on there? There will be, shocking, a question on divide and conquer, which will include the master, possibly include the master theorem. Okay? There will be a question on greedy. There will be a question on dynamic programming. There will be a question on NP completeness. There will be a question on graph algorithms, which means shortest paths, strongly connected components, topological sort. And there will be a wildcard question, which means I get to mix and match and do whatever I want. And I'm also thinking of posting maybe the day after a bonus question, which will be hard. I'm not sure about this. Maybe this is not a good idea, but because I don't want people trying to do the bonus question. What I used to do, which is not a good strategy, which is the hard questions are more interesting, so you try to do those first. This is the opposite of what you're supposed to do. You're supposed to do the easy questions first. But they're usually boring. So in order for people not to fail, I'm going to try to make these, definitely I'm going to try to make these easier than the fall. But I thought just for the people who are really want to do hard questions, maybe I'll post a hard bonus question. But I don't want you doing it when you should be doing these questions. So maybe I'll post it the day after or something. But then I hope it doesn't clash with the. I don't know how I'm going to do this. Maybe I'm just not going to do that. But it's also more fun for me. But maybe I'll post the. I don't know. I mean, if you want to do hard questions, you can always just do one of the programming competitions or something like that. Okay. These may all involve asymptotic notation. So big O, big omega, blah, 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 big theta, whatever. So now you know what's coming. You know what we've seen. The scribe notes are basically mostly up to like here-ish. It shouldn't be, it's a hard course. I mean, it's always a hard course. Algorithms is a hard subject. They tell me what this principles of programming language and one other course are like this wall of that is just really hard to get over in third year. I think most people will pass. I hope most people are doing okay. I'll try not to make it too hard. So I would thank you for being in my class. I would normally say that it's been fun. Well, sort of being a professor. I'm sure it would have been fun in a normal semester, except I haven't actually met any of you, and it's the most fun is seeing people sort of when they actually get this stuff, and sort of you see the light come on. And speaking of which, that's one thing I was going to say. I was looking at some of the stuff about NP completeness. Please remember for NP completeness, to show that something is NP complete, first you have to show that it's in NP, which just means that now that we know Cook's theorem, just means that you have to show that you can check a solution in polynomial time. This is generally easy. Not always, but generally. Usually. But then, the other thing to show that something is NP complete, you do not argue that You do not give an algorithm and show that it doesn't work. Okay? You do a reduction from a problem you already know is NP complete to this problem you want to show is NP complete. Because this means you do this reduction in polynomial time, you show that if you could solve your problem, then you could solve this other problem. Because given an instance of this other problem, you can turn it into an instance of your problem in polynomial time, such that this is a yes instance if this is a yes instance, if and only if. Okay? So that means that if you could solve your problem, you could solve HAMPath and SAT and clique and independent set and all the rest of them. Because you would, so say you do this reduction, so your problem is whatever. Okay, let's look at that project I posted. So that words2 thing, right? So is there some word, does this graph contain a word from this dictionary? And he did the reduction from Hamiltonian path in grid graphs, okay? So, which other people have shown is NP complete. He showed that if you could do this, so if you could solve words2, then you could solve Hamiltonian path in grid graphs. How? Because he showed that given a grid graph, he could turn it into this matrix of characters, such that and a dictionary which contained one string, such that this grid this grid of characters contained this string if and only if there was a Hamiltonian path in this grid graph. And so that way, if you could solve words2, then you could solve Hamiltonian path on grid graphs. And if you can solve Hamiltonian path on grid graphs, you can solve Hamiltonian path. If you can solve Hamiltonian path, you can solve SAT. If you can solve SAT, you can solve all the rest of this stuff. Okay. You do not just argue that you don't know how to do it. Okay, I was just looking at somebody's solution who was doing that. You don't say, this algorithm didn't work, or this algorithm didn't work. The only thing I can think of that works is trying all the possibilities, which takes exponential time. No, you don't try to argue that stuff won't work. You show that if you can do that, because we don't know, you're trying to prove that these things are hard. We don't know how to prove that P is not equal to NP. To do this, to show that your problem is NP complete, you do a reduction from a known NP complete problem. Okay? Sorry. Somebody wrote that I go on these rants, which, but this is my last chance to set you straight about this. So and look, you know there's going to be a question about this. Now, you also know that your worst question is going to get dropped. So, but you don't know what this question is going to be like. So you should at least practice something about NP completeness. Try to learn that stuff. It's also, as a future computer scientist, this is sort of a very key concept. At this point, I would be saying normally, are there any questions? Oh yeah, so getting back, I wish I could say I've really enjoyed being your professor. Interacting with you as much as I could, that was as fun as I think it can be when I don't actually see anybody and I can't see the light come on, and I don't know what anybody sounds like. I don't know what anybody looks like. This has not been a fun semester to be a professor. It hasn't been a fun semester for anybody. In the university outside, it hasn't been a fun semester for anybody, I think. Good luck. And I hope, well, you know what I look like, I guess. So if you see me wandering around campus, please say hi. I probably won't recognize you, But tell me who you are, and I might recognize your name. And yeah, when people are back on campus, so maybe in 2021. If I don't see you before you graduate, congratulations. And okay, so now I'm at 70 minutes, so I can let you go 10 minutes early. Good luck.